Okay?
Yeah.
Great. So, since this is the first day of the summer school, I thought maybe I should know the audience a little bit better. So maybe I'll do a quick survey here. So how many of you are graduate students? How many of you are postdocs? Okay, so a few postdocs, more graduate students. How many of you are from Hong Kong or working in Hong Kong, go to school in Hong Kong? Okay, a few. How many of you are from mainland China? Okay, a lot from mainland China. What other places are you from? Taiwan? We have one from Taiwan.
We have one from Taiwan.
You're 5 from Iran. I hope you didn't go to my talk. Did you go to my talk today as well? No. Good. All right, good. So there's no overlap here. Any more other countries? You're from Japan, right? Anyone from Singapore here? No one from Singapore. Oh, yes, there's one from Singapore. And any from India? No one from India? Oh, there's one from India. Okay. All right, great. Okay, so this is a summer school. It's not a conference. So there is no fixed set of material I need to cover. So if you have any question about what I'm talking about, just ask the questions, and we will take it from there. Also, I will be around until Wednesday. So if you have any questions you want to discuss with me afterwards, have a chat. That would be great too. The goal of the workshop is for you to be, the summer school is for you to be able to interact with each other and with us, yes? Okay. So today I want to talk about, the topic of today is high throughput sequencing, the microscope in the big data era. So I try to throw all the buzzwords into this title to make sure that actually people come to the talk. So there's biology, and there's big data, and there's me. Okay, all right, maybe not. Okay. So what is high throughput sequencing? So what is sequencing? Sequencing refers to sequencing the DNA, okay? So as we all know, an individual, an organism, is defined to a large extent by its DNA, which is a sequence of so-called nucleotide A, G, C, T. Okay, so 4 types of nucleotides chained together, 3 billion of them forms a whole sequence called a DNA sequence. So there has been something very exciting going on in this area in the past 10 years. And this chart shows the excitement. The first time a human was sequenced happened in the beginning of the 21st century. At that time, it cost a lot of money, about $100 million, to sequence the human genome, because no one has done it before. It was the first time. But since then, the cost of sequencing a human genome has plummeted about 5 orders of magnitude. And recently, a few weeks ago, in fact, it was announced by one of the leading sequencing companies called Illumina that it costs about $1,000 to sequence the human genome. Okay? So therefore, with this advanced technology of sequencing, there comes a lot of excitement about applications to biology, to health, etc. So this is our Moore's law. Moore's law says that every 18 months, the cost of electronics reduced by a factor of half. Okay? And this is what drives the areas that we are excited about, communication and computer. Okay? And what happens here is that the revolution here in high throughput sequencing is going down even faster than Moore's law. We know that for us who works in communication for many years, the Moore's law is our technology driver. That is, without Moore's law, all these interesting ideas that we have, the theory we have, the algorithms we have, will be of no use in practice because it cannot be implemented. But with Moore's law, it enables a lot of interesting development. So I hope that with this technology revolution, also many interesting ideas can happen. So the basic problem of high throughput sequencing works like this. So this is my genome, 3 billion symbols long. Currently, there is no single technology that can sequence the whole genome from beginning to end because it's chemically too unstable. Very difficult to do that. Impossible. No technology right now can do it. But however, what current technologies do, most all the current technologies do, is the following. It fragments the very long sequence into many, many very short sequences. These short sequences are overlapping, and each of these sequences is forward read. Okay? So the output of a high throughput sequencing machine experiment is given by hundreds and millions of these short fragments reads. And the algorithmic problem is to take these sequences and try to assemble, recover the original DNA sequence. So basically, one reason for the revolution of high-throughput sequencing is that there are many multiple technologies. So back in the beginning of the Human Genome Project, there's only one technology called Sanger sequencing. So Fred Sanger won a Nobel Prize for discovery of essentially DNA sequencing technology back in the 70s, I believe. And based on his ideas, the first sequencing machine was built. Okay. But since then, there has been multiple companies have come up with their own different sequencing protocols through different biochemical processes. Yes. Okay. All right. Shall I start again from the beginning? No. No, sorry. You was up to me then, no. All right. So different technology uses different chemistry, basically, to do the sequencing. But from us, algorithmic people, the thing I want to get to is two different things. One, the read length. So this is the length of this short fragment called reads. In Sanger sequencing, the read length is about 10 to the 900 base pair. A base pair is the same as a nucleotide, a symbol. And these technologies all have different lengths. Some are medium, some are kind of short, and some are much longer. Okay, so this PAC-BAR, for example, has sequence read length of the order of a few thousand. Different technology also have different error rates. So as we know in communication, every measurement is prone to error. Whatever you measure, there's error, basically. And DNA sequencing is the same thing. When you measure an A, there's an error, there's a probability that an A will become another symbol, a G. And these are different error rates of the different technology. Okay? Different technology also have different throughput. So this is the amount of data you generate, the reads you generate from each run. Okay? So in Human Genome Project, a Sanger sequencing platform generates only very little amount of data. And that's why it takes a long time to sequence the human genome and costs a lot of money. Whereas current day technology like Illumina generates a terabyte of data, one sequencing run. And so that's why this is called high throughput sequencing, because it's generating a lot of data in a very short time compared to traditional Sanger sequencing. Okay? So what is exciting about DNA sequencing, high throughput sequencing technology, is that not only it can be used to measure a DNA sequence, okay, It can also be used to measure a lot of different biological information that the biologist or the doctor is interested in. So basically, the biologist or the chemist came up with interesting ideas on how to convert many different biological measurement problems into a DNA sequencing problem, and then apply this high-throughput sequencing technology to generate a lot of big data. And from this big data, one tries to design algorithms to try to infer from the big data the biological measurement of interest. So this is the general pipeline, and that's why I call high-throughput sequencing the microscope in the big data era. Because like the traditional microscope, it can be used to measure many, many different things, and not just one thing. And these are examples of things that you can measure, okay? What is more interesting, very interesting, is that the DNA sequence is basically a static footprint or a blueprint of life. The DNA sequence does not really change much throughout our lifetime, and each person has their own unique DNA sequence. So it's pretty static. But many other quantities that the biologists are interested in measuring can actually be dynamic. They vary over time, maybe depending on the state of the human being or state of the organism. And they can also vary spatially. Okay, for example, an example we come out is RNA sequencing, which measures RNA expression. And what this means to us is that basically that means with this kind of situation, now you have many, many measurements that you can make, and therefore a lot of data that you need to process. And that's where we come in, okay? So we are more of a computational or algorithmic or information-based people. We're not chemists, we're not biologists, but because of this generation of huge amount of data and the need to process this data to get information, interesting problems that we are perhaps more attuned to arises, okay? In particular, there are sort of three types of problems that one can think about this high throughput data. The first one is measuring the data. So the measuring data is essentially the basic problem of assemble the sequence based on the fragmented high throughput data. So each single measurement is computationally very expensive because you don't get the whole sequence all at once. You get only small fragments. And this is the assembly problem, okay? And the assembly problem comes in two flavors. One is assemble de novo. That means you are sequencing, for example, a new species or something very new that you don't have any prior information about. Or you may be assembling something that is quite similar to what you already sequenced earlier. For example, if I sequence a new human, I already have a sequence of an existing human because many humans have already been sequenced. Then I can use that information to do so-called reference-based sequencing or reference-based assembly. When you obtain all this data, the second stage is you want to manage the data, and that involves problems like compression and privacy. And lastly, you want to utilize this data to do something interesting. So just to give you one example is so-called genome-wide association studies. So you measure the DNA sequence of an individual, you look at the variation of that sequence compared to an average human individual. At the same time, you measure some phenotypical information about an individual, like, for example, the height, the skin color, what illnesses, what diseases it has, and try to draw a correlation between the variation with what you observe. And if you draw a good correlation, then you can use that to predict in the future based on the genomic data. So there are a lot of problems there. All of them essentially are dealing with the sequencing data. And with the high throughput sequencing data being more and more popular, there are more and more such computational problems. Today, due to limited time, we're going to focus only essentially on this measuring data. And in particular, I will focus on essentially the assembly problem, de novo. But I'll focus on two types of assembly problems. But before I talk about the specific assembly problem I want to talk about, let me give a little bit of a philosophical view on how people have looked at the assembly problem in the past 10, 15 years. Okay, because as I said, Human Genome Project, the first time human genome was sequenced was 15 years or 10, almost 15 years ago now. So there has been a lot of work done on building assembly algorithms. And there are 3 points of view. 1, software engineering. 2, computational complexity theoretic. And 3, information theoretic. Let me briefly say something about each. As I said, each sequencing run generates a lot of data. Primary concern of the assembly programs are essentially to minimize time and memory requirement. What is lacking in a lot of this work is that there are really no guarantee on how good the output of the assembly is. If you work on internet, then you know that a premise of the internet architecture is to provide so-called best effort service. Best effort means that you do the best you can do. Similarly here, these assembly programs are all, many of them operate on a best effort basis. Okay? So there has been also a lot of other work on some theory work on trying to figure out how to look at the problem from a theoretical point of view. Okay? And I'll briefly mention a little bit later on, but essentially a lot of these problems are trying to formulate the assembly problem as some kind of combinatorial optimization problem of different sort. These combinatorial optimization problems are typically NP-hard and even hard to approximate. Okay? But the most basic problem that this approach does not address, which we're interested in, is it doesn't address the question of when the solution, that is the output of solving this optimization problem, will reconstruct the ground truth. Okay? What does the ground truth mean? The ground truth is the underlying DNA sequence, for example. And you want to know when the solution reconstructs the ground truth. And that leads to the question that we asked when we started working on this problem a few years ago. So we start asking the problem from an information theoretic point of view, which is the question of the following. Okay? Which is, if I'm interested in reconstructing the genome, then how much data, how much read data, and how good the read data needs to be, the quality of the read data needs to be? Well, in order to reliably reconstruct. Okay? So you can see that this question is quite analogous to the question we asked in communication. In communication, what do we ask? Okay? We ask, if we want to communicate at a certain rate, how good the channel needs to be in order that we can reliably decode the transmitted message. So here you can think of the DNA sequence is like a transmitted message. What I receive is a bunch of read data, hundreds of millions of read data. And now I want to decode the message. And so I want to decode it reliably. And the question is, how much measurement do I need in order for me to be able to decode? Okay? And how good the channel has to be for me to decode. Okay? So that's the question we're after. And what we'll show is that by answering this question, it will lead to interesting algorithms that achieves the optimal answer to this question, which is what's the minimum amount of data I need to reconstruct. And by answering this question, we generate new algorithms, and these new algorithms have potential to compete or do better than existing state-of-the-art algorithms that others have developed through the other. Okay? And I would like to show you some examples of that. In particular, this tutorial will focus on two assembly problems. One is the DNA assembly problem, and one is the RNA assembly problem. Okay? I would like to emphasize two themes here. One is the interplay between information and computational complexity. So these are big data problems. To solve big data problem, it's not enough just to look at the information point of view. One also has to look at the computational point of view. And it's the interplay between these two points of view I think is quite interesting and quite relevant in a lot of other big data problems as well. So I'd like to highlight a little bit about this. Two is I want to highlight the role of using empirical data in driving theory and algorithm development. So in communication, we're all very familiar with basic models, like, for example, the additive white Gaussian noise channel. Okay? Nobody really doubts the importance of these channels when you use them. And so a lot of our work in information theory and communication are of theoretical nature, in the sense that you don't really have to go and measure the real world to validate your theory. You basically just use models that's well established, like the Gaussian noise channel, and you do theory based on that. In this genomics area, since it's relatively new, we don't have such well-established model. So therefore, it's often interesting to draw a direct connection with the empirical data. That is the huge amount of data that has already been sequenced out there of genomic data. And we can use that to our advantage to validate or to connect with our theory and our development of algorithms. And the empirical data provides guidance for us to decide which algorithms are good and which algorithms are not so good. Okay? And I'll show you how we try to do that. Okay. So now let me move on to part one of this tutorial. Okay, which is on de novo DNA assembly. Okay? All right, so now I'm going to go to more detail. And so if you have any questions about what we're doing, please do ask me. Just want to get home during my time. So I talked for 12 minutes already. Okay. Actually, I talked for more than 12 minutes. I think you reset me sometime in the beginning. Okay. All right. So here is the assembly problem. We need a model to do theory. So here's the model. A very long sequence. The genome length, I always call variable G. So I'm very bad at remembering notation. So that's why in my talk, I usually try to minimize notation, because I thought maybe other people are not that great in memorizing notation as well. So I'll use very little notation. But I will use these three variables rather often. And so let me remind you by writing it here. Okay? So I have G, which is, if you don't mind, I'll erase the name and Piazza as well. Okay. So we have G, which is the length of the genome. By the way, the word genome and the word DNA are used interchangeably. Okay, the length of the DNA, G. In human, G is about 3 billion. In other organisms, G may be shorter, may be longer. Okay. The second variable I'll use is L, which is the length of each of those fragments called reads. Okay? All right? So depending on technology, L is different. For example, in Illumina, L was around 100. In PacBio, L was around a few thousand. So this is a key parameter that varies from one technology to another technology. And lastly, we have N, which is the number of reads. Okay? All right? So we'll use a very simple model for the read generation process. This model is used quite a bit. And the model is the following. Each read is assumed to be uniformly sampled from the entire sequence, and different reads are independently sampled. Okay? Is that more clear? All right. Okay, so this is the question, or this is the model. We have n reads, each of length L, uniformly sampled from the genome sequence of length G. Okay? This picture captures essentially the essence of the problem. Now, this is a very basic model, and there are different variations of this model, which I'll say a few words about. One is that the read length L here is assumed to be a constant. That means each read is the same length. However, there are some technologies in which the read length is variable. Okay? But it turns out that one can extend to that setting as well. So we keep it simple, and we fix the read length L. There are also other situations in which the reads may not be completely uniformly sampled. There may be some unevenness of the coverage or the sampling of the reads. Okay, one can consider that extension as well. But here, we'll just focus on the uniformly sampled read throughout the lecture today. Okay? All right. So, what is the sampling problem? The assembly problem is to reconstruct the genome, the underlying sequence, given the reads. That's it. That is the question we want to solve. Very clean, simple problem. So this is the most gigantic, largest jigsaw puzzle problem in the world. You have 100 million of these pieces, okay? And you want to put them together like a jigsaw puzzle to get back the original picture. What is more interesting, most interesting about this problem is that, you know, in jigsaw puzzle, they usually give you a box, right? That box has usually a picture there, and you use that picture as a guide to put together a jigsaw puzzle, yes? I threw away the box as well, just to make the problem more interesting. Okay, so no box, just the pieces. You got to get back the original picture. And it's not a few thousand pieces, it's hundreds of millions of pieces. Okay? That's why it took 10 years to solve this problem in the first time around. But now it's taking a bit using a computer. Okay? All right. Okay. So, tell me, when you do a jigsaw puzzle, how do you put the pieces together? What do you use as a clue to put the pieces together? You don't know how to do jigsaw puzzles? The overlapping portions, right? So in jigsaw puzzle, the pieces are not really that overlapping, but what you use is similarity between adjacent pieces, right? To try to fit things together. Here, there's actually a little bit more than just jigsaw puzzle. The adjacent pieces are overlapping. And you're using overlapping portion to give you a clue that these two pieces should fit together. Okay? So that's the basic approach, or the basic information that is available to you to put the pieces together. But the problem is not simple. And there are two particular challenges. Number one is that on the genome, there are a lot of very long repeats. It turns out that nature, in the evolution process, like to duplicate parts of the genome to elsewhere, so that there are different parts of the genome which looks very similar to each other. As every puzzle person knows, this is bad news. Because if you have areas of the picture look similar, then it leads to more confusion. Okay? And this is an example of the length distribution, and you can see that on human chromosome 22, for example, there are repeats of length more than 1,000. Okay? So you have a long stretch of the DNA, which is identical to each other, but in two totally different parts of the genome. Okay? And secondly, normally you have long repeats. Okay? You also have errors. Errors is like what? It's like when people make the jigsaw puzzle pieces, they intentionally corrupt some of the pieces and make it doesn't look like the original picture at all to confuse you. Okay? And this is an example of a read error profile, and you can see that the read errors can go up to, say, 1 or 0.1%, okay, for this particular technology, and some technologies more errors, okay? All right, so here's our approach to solve this problem. Like a good theoretician, we make some simplifying assumption, which is kind of ridiculous, on first sight. So first, we'll assume the reads are noiseless, just to focus our problem on the repeats. In this simpler problem, which is noiseless read, we will derive some fundamental limits. In other words, we will show that there are some intrinsic limits to what any assembly algorithm can perform, and we'll derive algorithms, assembly algorithms, that provably is near optimal on the data of interest, on the genome of interest. How I do that, I'll show you later. Then we'll add back the noise into the picture and see how things change. Does noise make the problem much more difficult, or it makes the problem slightly more difficult? We will address that issue to some extent. Okay, just to give you a picture, view of the situation. Here are two jigsaw puzzles. Okay, here are two jigsaw puzzles. Which one is more difficult than the other one? How many people think the left one is easier? Left one is easier? No. This one is easier, right? Because this one has a lot of repeats. So if you have a piece here, then you don't really know whether that piece comes from here or here or here or here. You have many uncertainties, and therefore causes confusion, and therefore requires, in some sense, bigger pieces for you to work. Here, there are many different parts of the picture which looks very different, unique, and therefore makes the assembly problem easier. Okay? Now, what we're after as information theorists is the following question, which is, we know that the difficulty of a jigsaw puzzle should depend on how much repeat there is in the jigsaw puzzle. So what we want to derive right now is exactly, precisely, how the fundamental limits depend on the repeat statistics. Okay? So that's the question I'm after. Okay, before I address this question, let me say a few words about how people thought about this problem of deriving fundamental limits to the assembly problem before. And there was a famous paper in 1988 by two people, Eric Lander and Michael Waterman. These two are very famous people in this area. They asked the following question. This is in the beginning of the Human Genome Project. The Human Genome Project started in the early 1990s. So this was just at the cusp of people start thinking about sequencing. So they were asking the following question. They said, well, obviously I have to ask a very simple, obviously they're faced with this basic question, right? Which is, how many reads do I need for an assembly project? So they start asking this question, which is, well, they figure, in order for me to assemble something, I should have a good coverage of my underlying DNA sequence, right? And so they ask the question, which is, if I want to cover the entire sequence with, say, probability 99%, okay? How many reads do I need? Can anyone answer me, why do we need this probability 99%? Why not probability 100%? Isn't 100% better than 99%? Why can't I just have this epsilon to be 0? Sorry? Because the reads location are random, right? So therefore, there's always a chance that no matter how many reads you sample, let's say you sample 100 million reads, there's always a chance you miss out some parts of the DNA just because you're unlucky. So therefore, there's no guarantee. And so no 100% guarantee. And so you should step back and say you only want 99% guarantee or 95% guarantee. Okay? All right. And the answer to this question. Do people know how to do this calculation? What is the basic idea here? Is there any problem that you're familiar with that is similar to this problem? I'm supposed to assign questions, right? Is it? Okay. So my question is, if you go back to your basic probability, there's a problem called a coupon collection problem. What's a coupon collection problem? Do people know the coupon collection problem? Yeah? So think about the genome, a very long sequence. We have reads of length L, and let's just simplify the problem by chopping up the human genome into many reads, many parts of length L. And the coverage problem becomes roughly saying that you want to collect every single segment of length L from the human genome. However, each collection is random, and so you may collect after n. So let me ask you a question. If I have a genome of length G, okay, and I chop it up into segments of length L, okay? How many samples do I need to collect before I get back the entire sequence? In other words, I collect every single segment of length L. Okay? Let's count. What's the length of this whole sequence? This is the test whether you're paying attention to what I'm saying. G, right? Don't be shy. You're in the school. You're in school, you should ask questions and make mistakes. It's fine. I make mistakes all the time. G. How many of these sections are there? G over L. Right? So therefore, at least I need to collect G over L samples, right? Before I have a chance to get the entire genome, right? Do I need more? If I collect only G over L times, do you think it's enough? No. Why is it not enough? Because it's random. If it's random, there's a chance that I may collect one particular segment twice, just by random bad luck. And if I collect something twice, that means I missed out something else that I could have collected. So that's why this is called coupon collection problem. Think of all these guys as coupons. Each time you randomly collect one of them, and now the random coupon collection problem tells you how many coupons you need to collect in order to guarantee the probability 1 minus epsilon that you get all the coupons. Okay? And it turns out that the answer to our question is what you're supposed to calculate, maybe in your break or from now to Friday. I don't know how you're going to work these homework questions. All right, good, all right. And it's given by this expression, which your homework question is to verify. Okay? Something like that. It's approximately like that. Not exactly, but approximately like that. Approximately in the sense of for G very large, okay? Because G is very large. And you can see that the actual number of coupons you need to collect has an extra logarithmic factor, log of G over L epsilon, okay? And this logarithmic factor is the extra number of reads you need to collect in order to guarantee that you have coverage. Okay? So this is a number which I will call Lander and Waterman number. LW. Okay? Named after Lander and Waterman. Okay, good. All right. So tell me, have these people already answered the question that I'm interested in asking? They told me that if I collect this number of samples, reads, then I can cover the whole sequence with probability 1 minus epsilon. So, am I finished? No. Why am I not finished? So covering is a basic requirement, right? It's a necessary requirement. But I still need to stitch them back together to figure out which the locations of these guys, right? Because I'm collecting samples, but nobody's telling me that this sample comes from this particular part of the DNA. I need to put it back together, and that's where the overlap is useful. Okay? So Lander and Waterman number only provides a low bound. And in particular, Lander and Waterman number and LW does not depend on the DNA repeat statistics. This number is given by this formula has nothing to do with how complex the DNA is in terms of the repeat statistics. In other words, in terms of our jigsaw puzzle analogy, we don't know whether it's the left picture or the right picture, right? So somehow this must enter into the story, the DNA repeat statistics. Okay, so to solve this problem, we are going to do a warm-up exercise. What's a warm-up exercise in research? In research, we try to solve some real problem that is of interest to people, right? However, often, before you can solve a real problem, you solve an artificial problem first. Why do you want to solve an artificial problem if you have a real problem out there? That sounds rather convoluted. Well, first of all, you may be in a rush of publishing a paper. So then you quickly solve a, no, that's not a good joke. All right. So why do you want to walk through a warm-up problem? Is because you want to solve an easier problem first in order to get your brain moving. And then when you solve an easier problem, maybe it gives you a clue as to how to solve the harder problem. So that's what we did. So here is what we did. To solve an easier problem, we start with an easier model. Yes, a lot. You're worried about that. Yes. Yes. So Professor Alon Olinsky has highlighted a point that is very important. That actually is not very important, but highlight a point that I neglected. Okay. That means he's paying attention, and you guys are not paying attention. So what is he trying to say? He's trying to say that this is crap. This is not correct. In fact, I did lie a little bit. So if you think about it, there's some asymmetry in this problem, right? Because the edge is actually harder to cover. I need actually more reads in order to be able to hit the very first point and the very last point. Okay? True. So the two ways of getting around that. One is you can make everything symmetrical by thinking of this long sequence as a circular DNA. That would avoid the symmetry. That would keep the symmetry, and this expression will be correct. Another interpretation, another way of dealing with it is you say, well, I'm not really care about very small parts of the beginning or the end. As long as you get back to the sequence, as long as you cover the sequence from me, most of it, except for a very small part of the beginning and end, I'm happy. Why? Because when I sequence a genome, maybe I don't really care about missing a very short part of the beginning and a very short part of the end. Okay? So I will keep those two interpretations a bit vague. But bearing in mind that you use those other two to make essentially this rigorous. All right? Okay? All right. Yes? Yeah. So you can also use that. But here the model is that your looking read with starting position uniformly on this thing. Yeah. You can use a midpoint, yes. But it's not very important. It's not a very important issue, but it's something that if you want to be really rigorous about, you have to deal with. Yes. Okay. All right. So here's the toy problem that we solved, which was our starting point of addressing this problem. So a toy problem essentially means you. So here, so far, what am I missing here? Okay. What I'm missing here is a model for the repeat statistics, right? I haven't told you what a DNA looks like. So therefore, to start working this problem, the first thing is to make some assumptions about what the DNA looks like. And the simplest assumption that one can make is just to assume that the DNA is an IND string. In other words, AGCT follows a certain distribution marginally, and is IND throughout the genome. Okay? So we make this assumption. And being a good information theorist, we take some asymptotic, and we make the read length very long, and in fact it is very long. G is 3 billion, so pretty close to infinity. And we solve the problem in that setting. Okay, where's the point of solving the problem? Okay, so you remember that there are two things I'm interested in understanding the difficulty of assembly problem. One is the quality of the data, and second is the quantity of the data, right? So quality and quantity. Okay, these are two very important concepts. It's like you write papers. Quality is how good each paper is. Quantity is how many papers you can write. Yes, we all understand that concept. Good. I think that is draw some connection there. In this assembly problem, you have a lot of data. Right? You have a lot of data. The data is the read data. What describes the quantity of data is clear, right? What's the quantity of data? How many reads you get, right? The more you get, the larger the quantity is. But what's the quality of the data? Well, each read has a quality associated with it. Can anyone think what is the key parameter that describes the quality of a read? Suppose I give you many reads, but each read is only a single symbol, a single nucleotide. Is it very useful to assemble, to put together to get back the original DNA? No, right? Because if it's very little, then I can overlap to put back together, right? So therefore, an important measure of quality is what? It's the length of it, right? The longer the read, the higher the quality. Okay? So there you go. We have two axes here. One is the read length, and two is the number of reads. This two axes is going to be my picture throughout this talk, basically. Two dimension, read length and the number of reads. In the number of reads, I already have one number that I know is the baseline. Baseline means the minimum number that I need is called NLW, Landau-Waterman number, given by that expression. So what I'm going to do is I'm going to normalize the number of reads I need by this Landau-Waterman number. And this will tell me how many reads do I need, more than Landau-Waterman, in order to assemble this IIDG. Okay? So this one is my baseline. All right, so here's the solution of that problem. So first, below this line, there's no coverage. There's gaps. And that's no good. That means here, you can definitely not assemble the genome, right? Now, about this line, this coverage, there's hope, but no guarantee. It turns out that in addition to length of Warman, there's a second line that's important. And this second line is given by a number which is 2 over the Rene entropy of the string. Okay, this is a number they can calculate from the IID distribution. The exact expression is not very important. Log G. Okay? And if you calculate this number and draw a vertical line, what you will find is the following. On the left of this line, then you will find many repeats of length L, which is less than this number. On the right of this line, you will find essentially no repeats of length L. Okay? This is for the IID genome. So this line is a dividing line between log repeats and no repeats. Okay? So that means the repeat complexity is described by essentially this number, which is the longest repeat you'll find in genome. So now, what do we know? Well, first, we know that below this line, you cannot get assembly because there's no coverage. Also, on the left of this line, because there's so many repeats of length L, and your reads are less than L, it turns out that you're too confused, you know? Because if I give you a read length L, then you don't really know where to put this read in the jigsaw puzzle. So you're confused. And so red means no good, no assembly. And what we showed is that as long as you are on the complement of the red, then you can assemble. And in particular, you can reconstruct using a very simple algorithm, which I'll talk about later, called a greedy algorithm. Okay? And so this completes the solution of the IID problem. So we're very happy with the solution. We start high-fiving each other. So in high five, you know high five. Everyone knows high five. We're very happy. However, when we show these results to our friend in computational biology, we got less excited. And the reason is that when you actually look at the real data, okay, so you go to, there are now several so-called genome browsers around the world. One is by UCSC. You can go there and actually find sequences of genomes of human, of different organisms already sequenced in the database, and you can find them. So this is one example of the human chromosome 22. Its length is 35 million long. And so we thought, okay, we have an IID model. Let's see how good the IID model is in terms of predicting the repeat complexity of human chromosome 22. And so here's what we do. We go and look at the length, and we actually measure how many repeats of length L are there in the data on human chromosome 22. Because this chromosome has already been sequenced pretty reliably. So we can use that to measure how many repeats there are. Actually, we're going to search the number of repeats. And this is a plot of the number of repeats on a log scale as a function of L, the length of the repeat. Okay? All right. So what does it mean by L repeat? I'm going to use this concept quite a bit later on. And so this is the picture. This is my human genome. If I find a segment of length L and another segment of length L of the same string, then I call this one occurrence of a length L repeat. Moreover, I only count repeats that are maximal. In other words, you cannot extend it in either direction and get a longer repeat. Okay? This is just a good thing for me to do for accounting purposes, so I don't double count repeats that are within each other. Okay? So I now count on the genome that's already sequenced in the database. There are programs that allow you to do that. How many repeats of length L are there for each L? And then what I do is I take the human genome, chromosome 22, And then we randomly shuffle all the symbols. Okay? Randomly shuffle all the symbols means essentially we break down all the correlation, and we do an IID fit. And then we measure the number of repeats in the randomly shuffled sequence. This is like fitting the IID model to the chromosome 22. And we look at the data and we say, hey, wait a minute, actually, it's pretty good. The IID fit is a pretty close fit to the data, as you can see. No, AGCT is about 30%, 30%, 20%, 20%. Yeah, an IID with distribution does not have to be uniform. Okay, IID means it's independent, identically distributed across different genomes. Okay? All right. But as you can see, we're only up to L equals to 10 and 12 here. So let us zoom out a little bit. And now I'm out to 14, 15. And I'm now zooming out to 160. You can see that the actual data shows a deviation from the IID fit. Okay? And this is what I'm referring to as long repeats. So in other words, if you use an IID model, you would predict that the longest repeat is at about 25. Whereas in the real data, you see a lot of long repeats even up to 170. And in fact, as you've seen already, that actually the longest repeat goes up to 1 or 2,000. Okay? So this is a cause for concern for our IID model. We're not very happy with that. So this is the first point in which a theoretical model that we use does not really jive with the actual data that we confront with. Okay? So then we start thinking. How are we going to extend our theory, well, a very nice theory, to deal with actual data which looks like this? And that leads us to a different approach to this problem, what we call individual sequence approach. And we'll take a 5-minute break, and then we'll come back and I'll explain to you what we mean by this individual sequence approach. And we'll see that the results we get there has, although some similarity with the IID result, there are many aspects which are very different. Okay, we'll be back in 5 minutes, and then we'll continue.
Recorded this one or recording this one. Okay, can you zoom in this screen? Extend out. So Which one do you think I should record? We should use the desktop because we have to zoom in. Can we zoom in to previous page? This is okay. Okay, go look at her.
Shall we continue?
Up to you. Yeah.
All right. Okay. All right. So let's continue after a break. Okay. So we were at this point where we had solved the problem for the ID genome, but the ID genome is not a good model for the actual genome. And so we needed a sort of different approach to the problem. And the first approach that one can think of is perhaps one can come up with a more sophisticated model, statistical model of the human genome, and perhaps extend our theory to that more complicated model. Well, unfortunately, we ask around, and there's just no well-established model that anyone can agree on that can capture these very long repeats. So therefore, we decided not to use a statistical model, but rather try to be able to derive some fundamental limits based on the sequence itself. So you give me a sequence, okay, this could be one particular the human genome, and I can tell you some of the fundamental limits and the performance of algorithms on this genome. So let me explain a little bit more about how we do that. So here's the problem. In this paper we wrote last year, okay, with my student, Guy Bressler, you can see that the authors are Bressler, and Shea. This is not hyper. This Bressler has a twin sister. My student has a twin sister. And this is the brother and sister pair. Now, there's some interesting coincidence about this whole thing. This whole paper, remember, is about what? What's the main theme about this work? Repeats. It's kind of bizarre, but it happened. All right. Anyway, so just to make sure along Professor Olisky didn't miss a joke, I was saying that this whole work is about repeats. And we have two twins working on, a pair of twins working on this problem. So it's a perfectly apt. So you witness they're actually twins and not some gimmick that they were trying to report to me, right? Okay, so here's the approach we're going to pick, and I'm going to explain this approach carefully, because I think this approach may be useful for other problems as well. So you give me a genome S. So this genome could be, say, human chromosome. I got tired of 22, so let's switch to 19. Human chromosome 19. And from S, I'm going to extract a bunch of repeat statistics, like this picture. And from this repeat statistics, I'm going to be able to plot, again, in my same axis, read length and number of reads, and length, some curve, okay, which has the Landon-Woodman low bound here, but has a vertical bar, which is a lower bound, okay, on the performance of any algorithm, okay, for assembling this, okay. This low bound is a little bit tricky, but I'll explain it more later on in this slide. But this low bound gives you a measure of the fundamental limit on any assembly algorithm. And then what we're going to do is we're going to look at a few basic assembly algorithms, and we can evaluate the performance we get from, say, an algorithm called greedy. Okay? So what does this curve mean? It means that this algorithm would need this much read length and this much number of reads in order to assemble the genome. You can see that this algorithm is pretty far away from the low bound. And then we'll find that another algorithm called De Bruin, which I'll explain later as well, gets closer to the low bound, but still there's some gap. And then another algorithm, closer, but still some gap. And finally, we came up with a new algorithm called multi-bridging, which gets very close to the low bound. Actually, there's a little bit of gap, but it's not. Yes. Well, actually, that's not the case. So the genome is actually used. The first human genome was sequenced using Sanger reads, which got to be around 1,000 or so. So the question is, how do you see repetition of length 2,000, although you are only using sequence technology about 1,000? That's a very good question. I never thought about that. But actually, we do find such long repeats on the reference UCSC browser. So there must be some other ways for which they piece these things together. Maybe what they do is they use human intervention, actually. They use some biological knowledge to actually piece things together in addition to the high throughput or low throughput data. But that's a very good question. I'll dig a little bit deeper into that question, hopefully come with a more satisfactory response. But a lot of these human sequencing projects is to use various high-throughput data and also to mention together. Okay. But that's what we measure. We measure repeats of this kind of like.
You don't necessarily want just one reference. You say like there's a list of possibilities. Like it's kind of like list decoding rather than.
Right.
And that seems to be the metric that they go with rather than.
Yes. So, yes. So, in fact, most sequencing projects nowadays do not generate a single solution. So, generating a single solution is called finishing. So, there are some people with interest in finishing, but because the current state of the art deals with pretty short reads, finishing is still quite far away. And so, one possibility is essentially people generate a bunch of contexts, and then they just return to you, say, a few hundred contexts, and they measure quality of the solution by how many contexts and how long they are. Yes. It's a little bit hard to do a theory based on that kind of output. We tried, but not very successfully. And so the cleanest theory we got is to assemble the whole thing. And hopefully, as we move to longer reads in emerging technologies, we're getting closer to this goal of assembling the whole thing, which is in some sense the ultimate goal. But good question. Yes, Chandra. Well, typically, so even this was simplifying, right? Because actually in practice, you're going to get a bunch of chromosomes, 22 chromosomes, all mixed together. And your read is a mixture of the data you get from each chromosome. Even this picture was just as an example. But really, there is kind of limited locational information that people make use of. Okay? All right. So this picture, together with these algorithms and this low bound, gives us a pretty tight characterization for this black curve, which kind of describes the fundamental limit of the problem. And I would like to draw particular attention to this number, which is this vertical asymptote of this black curve, which we call L critical. So this number, which is around 2200 for human chromosome 17, tells you how difficult the assembly problem is of this axis to read length. It tells you that if read length is below this number, then assembly is not possible. Above this number, if you are reasonably above this number, say 10 or 10% above this number, then you can get very close to the lambda element coverage, and you can assemble already. Okay? So there's this further out here called L critical, which I'll now describe. Okay? And we tried it out on many different types of data sets. Okay? And we find that very similar behavior with matching upper and low bound, also true for a wide range of benchmark data sets. Okay. So now I want to explain where the lower bound comes from. Okay. And then I'll explain, once we understand the lower bound, we'll explain how we can have algorithms that get closer to lower bound. Yeah. Alon? Yes. That's the point of this. Yes. If you're a single repeat, yes, you can reconstruct. Yeah, I'll show you later in the 2 or 3 slides. Okay. So here is the low bound. What is the low bound? Lower bound tells you that if something happens, then reconstruction is not possible. I'll show you why. So this is the genome, and this is a picture I'm drawing here. So what is this picture? So this red and this red is okay, and this yellow and yellow is another repeat. Okay, let's call this X. Let's call this X. This is X. One repeat. Let's call this Y. Y is another. So this is not a single repeat. This is two repeats, and they are interleaved together. What does it mean by interleaved? It means that the first copy of red occurs before the first copy of yellow. The second copy occurs after the first copy of yellow. They're interleaved together, and not red, yellow. If it's red, yellow. Okay, is that clear? Now, the blue ones are the location of the actual reads that were sampled. All right. I claim that if this is the actual situation, then reconstruction is not possible. In other words, there will be an alternative that is hard to distinguish. So here's the deal here. So one observation, you look at each of these copies, okay, then I call this a condition of no bridging. What does it mean by no bridging? It means that if you look at each of these copies, and you look at the reads, okay, then none of the reads will go from one side of the genome to the other side of the copy of the read. Okay? So you can see, for example, this read starts from here, this left side, and it goes to the middle of the repeat, but it doesn't go to the other side. Okay? So is it clear what I mean by no bridging? And all four copies are not bridged in this example. So now I claim that with this situation, there's another DNA sequence for which the likelihood of observing these reads is the same. Okay, so here's the animation. So this part of the DNA and this part of the DNA and the associated reads, okay, can be swapped. Okay? And if I swap them, what will happen? Let me do it again. Right? So this is the original DNA. I swap these two, and this would be a new DNA, right? And what can I say about the new DNA with respect to the original DNA? Well, because the reads, they don't go from the green to the blue region. They go into only the red region. When I make a swap, these reads looks like they can equally likely to come from the new sequence than the original sequence. In other words, you can show that the likelihood or the probability of seeing this set of reads is identical under the original sequence and the new sequence. And I call that an unresolvable situation. Okay? Is that clear? What's going on? Okay. So, therefore, a necessary condition for reconstruction is that you see this kind of interleaved repeats, then they should be bridged. All interleaved repeats should be bridged. Bridge means what? Meaning that at least out of the four copies, at least one of the copies should have at least one read that goes from the left-hand side to the right. Okay? All right. Now, how do you use that to get the black curve that I wrote down? So remember that we had a curve with a lower bound, right? So this lower bound was based on exactly that condition. And that's not difficult computation, right? Because what you have to show is basically, if I give you a DNA sequence, you basically have to show that you sample enough reads such that with high probability, with probably 95% or 99%, all the interleaved repeat will have at least one read covering it with that probability. That is not a very difficult calculation, and maybe that could become another exercise on Piazza, right? Is that what you do? You put the questions on Piazza? Is that how you? Okay, all right. So I won't do the computation. So that gives me the black curve. So let me ask you a question. This black curve actually becomes a vertical line, right? Can you tell me from what I told you so far, what is this vertical line? In other words, what repeat, what length, this number, 2200, what do you think it corresponds to? Let's put together. Okay. So remember that as the number of reads go larger and larger, okay, then what will happen if this length, okay. So what do you think I will converge to as goes to infinity on that curve? Okay. So basically, if you think about this condition, okay, this necessary condition implies that the read L should be greater than the longest interleaved repeat of the sort. Why is that? Let's try and understand that. This is kind of important. So if the read length L is less than the longest interleaved repeat, is there any hope that the longest interleaved repeat will be bridged? No, right? Because if the read length, even the read length is shorter, then there's no way you can represent red line. Suppose this example, N is the length of the longest interleaved repeat. Okay? If L is less than N, then there's no way you can bridge this interleaved repeat. On the other hand, if L is greater than the longest interleaved repeat, you can still get unlucky, and when you sample it, you still have no bridging. But definitely when L is less than longest repeat, then you'll definitely be unable to bridge. And as the number of reads gets larger and larger, then as long as L is greater than this number, then eventually you can bridge all interleaved repeat. Because as you sample more and more, then eventually you will be able to bridge all. Okay? So therefore, this vertical line, L critical, is actually just the longest interleaved repeat on that genome. Okay? Which is 2200. Okay? Yes? Yes. Sorry, I made a mistake. You're right. The minimum between M and N is the length of the interleaved repeat. The longest one is you take all such patterns and find the longest and the minimum of the two. Good. It's not M. I mentioned it. Right? So as long as the length is larger than the minimum, then as long as you get more reads, then eventually you will bridge this one. But if L is less than the minimum, then you cannot bridge any four of those copies, no matter how many reads. Okay, so you're right. Minimum is the right one, not maximum. Okay, so it turns out that the problem is a little bit more subtle. Because actually there is another lower bound. And this lower bound is incurred by triple repeats. So we have interleaved repeat and we have triple repeat. It turns out that these are the two. And we have exactly the same situation. All three copies are not bridged. Then again, you can swap the green and the purple, and you get an alternative sequence for which the likelihood of observing the read is low. Okay? So therefore, the necessary is that all triple repeats should be bridged. And again, you want the read length L to be greater than the longest repeat. Okay? Now, it turns out for this data set, this black line is the one given by the interleaved repeat. The triple repeat line is actually somewhere here, and therefore is not tight. Only the triple interleaved repeat was tight in this particular data set. And we'll come back to this point later on, the distinction between triple repeat and interleaved repeat. Okay? All right. So now we explain the low bound. The low bound is actually obtained by interleaved or triple repeat. In this particular example, interleaved repeat. Now, what about algorithms? So now I'm going to go through a few algorithms to see whether they could actually get to the low bound. Okay? All right. So here's the simplest algorithm that one can think of. Actually, at EASIT, this happened. Professor Waterman actually gave a plenary talk, and he said this algorithm is the one that everyone came up with after about 10 minutes. So now I give you 10 seconds. And after 10 seconds, we came up with this algorithm. So here's the algorithm. Remember that assembly is obtained by you exploiting the overlap between the reads, right? So what this greedy algorithm does is very simple. It essentially iteratively tries to merge the reads together to form bigger pieces. And then eventually, hopefully, grow the problem to one big gigantic piece, which is the original DNA. That's the hope. Let's see how it works. So the input is my set of reads and reads of L. Okay. The context is what I want to grow. Initially, it's just the reads themselves. Now, the first step I want to do is I want to merge the two pieces together to form one bigger piece. Which two pieces should I merge together? I want to merge two pieces together which I'm most sure that they probably come from the same area, right? They're adjacent to each other, right? Okay? So therefore, I should merge what? The one with the largest overlap, right? Because if two pieces have very large overlap, then there's quite high certainty that they come from the same place. Okay, so I find two contexts with the largest overlap and merge them into a new context. In this example, which are the two reads with the largest overlap? Can you see it? Actually, these two reads have the largest overlap because they are on top of each other. Okay? Because they're randomly sampled, so the chance of sampling these two reads from the same location twice. So I merge them together. Now I reduce the problem into one less read. Okay? Now, for example, this is more interesting. Now I'm taking these two reads, and now I find that they overlap to a very significant extent, maybe L-1. And then I merge them together, and I form a longer context. So this example was not very interesting because you didn't really grow it. You just reduce it into reads. But here I grow it because I'm merging length L to a read of length L, the overlap L-1. So the overall context I grew to is how long? L plus 1. So now it's longer. And I keep on doing this. over and over again. And every time I merge two pieces together and reduce the number of reads by 1, I get longer pieces. And eventually, hopefully, when I stop, okay, I will only have one contact remain. And if that's the case, then I will report the solution. Otherwise, I fail. I don't declare a solution. Okay? So this is the greedy algorithm. And it's the algorithm that you can think of. And the question I have now is, does the greedy algorithm get to the low band? And we already know for this genome that it does not get to the low band. And so now I explain what is wrong with this algorithm, what is missing with this algorithm. Okay. So now I need to analyze an algorithm. Right? So to analyze the algorithm, actually, all you need to do is to figure out in a clean way what is the condition for failure of this algorithm. When does algorithm fail? So let's look at this algorithm, and suppose I fail at, so when I fail, what does that mean? It means that I made a mistake when I merged two pieces together, right? So if I merge two pieces together and these two pieces don't belong in the same area, same region, and I merge them together, then I fail. So now I say, suppose the first error occurs when I merge this piece and this piece, and they have an overlap of length L, little l. Right? Suppose this is the first error. That means that all the mergers you've done before this, you were correct. And then you failed. Okay? So I want to know what that means. Okay? Well, it means two things. One is that there's a repeat of length L of the original genome. Right? Because if there were no repeat length L, then you would not have a matching suffix and a prefix here, right? But there's a second thing that is important. I claim that these two repeats, this repeat is not. Why do I claim that? Okay, suppose we argue by contradiction. Suppose this copy was bridged. What does it mean when the copy is bridged? It means that there's a read which goes from the left-hand side to the right-hand side, right? So, can this be possible? Can this be possible? No, it's not possible. Why? Because this one would have a longer overlap with this one than L. That means we would have already merged the purple one you will have merged these two together to form a longer concept before, and you would not have seen this green part by itself on the prefix, right? So that was a contradiction, and that means that what I was saying was correct. That is, either this copy or by the same argument, this copy cannot be bridged. So that means what? That means that if this happens, okay, what I'm saying is that if there's an error, then there's a copy of a repeat of length L, which is not bridged. So if you reverse the argument, then you is equivalent to say that if all the repeats on the genome are bridged, bridge means what? At least one of the two copies will read over it. Then this kind of error cannot occur, and therefore it really works. So therefore, this is a sufficient condition for the greedy to work. Okay? And now again you can decide which is how to compute how many reads you need and what's the read length you need to achieve this condition with probability 95% or 99%. And then you get a curve like this. Okay? And now we want to go back and answer Professor Alon Olinsky's question, which is, well, partially, which is what's the main difference between the greedy and the low bound? Why is there such a big gap? Well, first, let's try to figure out from this condition, all repeats are average. What does it mean in terms of the read length to satisfy this condition? If you want to satisfy this condition, how long do your read have to be? The read length have to be longer than the longest repeat, right? Otherwise, you will not reach it. So therefore, this vertical asymptote is actually the length of the longest repeat on the genome. But the lower bound is the length of the longest interleaved repeat. So what's the connection between interleaved repeat and repeat? Is the length of the longest repeat longer or smaller than the length of the longest interleaved repeat? Well, interleaved repeat is a specific type of repeats, right? And therefore, the length of interleaved repeat typically is shorter than the longest repeat. In fact, in this particular example, the longest repeat is 4092. And the longest interleaved repeat is at length 2248. So basically, this repeat here at 2248 is interleaved with this repeat at length 3000 something. But the longest repeat is somewhere here, which is by itself 4000. Okay? So therefore, greedy is confused at this point already, but the low bound says that we're here. So therefore, there's a gap. Okay? So now, once you see a gap, then you can ask the question, well, there are two possibilities here. One is that you can do better than greedy algorithm, okay? Which, related to Professor Olinsky's question, means that there is an algorithm which can actually resolve repeats. Or the low bound is loose, and therefore I should be able to push the low bound towards the right. And it turns out that the former is correct. That is, repeats that are not interleaved can actually be resolved by a more clever algorithm. Okay? So in the next 15 minutes, I'll explain 15-20 minutes, I'll explain how to do that. So what's the time we're doing here? Okay. So it's 10:41. You said there's coffee or something like that, right? At this point. It will stay. It will run away. The coffee. Okay. So let me do that. Okay. So I'll go a little bit more. Let me go 10 minutes more, and then we'll go for a coffee break, and then come back. Okay. So to study this question, we will switch a little bit to another model, which we call the dense read model. Okay. So you can see that actually those two curves differ to a first order in the vertical asymptote. So in other words, if I can look at a model which only focuses on the vertical asymptote and understand that situation, then I'll already be able to progress quite a bit in bridging these two curves. So let me now look at a model which just focuses on the vertical asymptote. How do I come up with a model that focuses only on the vertical asymptote? What does it mean when I say I want to study the vertical asymptote? Letting it go to the Do people agree with Professor Chandra there? You can disagree with him too, I think. You disagree with everything. If I let the number of infinity, then I'll get to the vertical line, right? Because the vertical line is one number of infinity. So let me do that. Let me construct a model now by letting n go to infinity. Okay? Now, What kind of information do you get when you let n go to infinity? Let's think about this.
Audience interaction chocolates or something?
Go ahead.
There will be coffee in 15 minutes, but anyone who answers questions, asks questions.
Oh, the coffee hasn't arrived yet. Oh, okay. All right. Okay. So in the shotgun model, when the reads are randomly sampled, then you get a read here, and then you get another read here, and then you get a third read here, and so forth, right? As I get more and more reads, what will happen? Everything I need to be bridged will be bridged, but in particular, what does it mean in terms of the reads on this DNA sequence? Everything will be read at least one time. In fact, everything will be read many times, because as n goes to infinity, right? That means red is harder to see than black. Thank you. Let's try black first. Okay. So it means that if I have a read length L, right, that means every position of length L, if I scan across the sequence, will be read, right? Because now n is going to infinity. Okay? Then every position I get will be read. And this information is what we call the L spectrum of the genome. Okay? L spectrum of the genome is essentially the situation where I have a read at every starting position on the genome. Okay? So this is equivalent to I give you a read here, a read here, a read here, a read here, and so forth. And it goes all the way down the genome. So this is more information than just giving you a random set of reads. Okay? So therefore, to understand the gap between two, I want to focus on this model. Okay? So the key question now is what is the minimum length L for which the genome is uniquely reconstructible from its L spectrum? So the L spectrum is the collection of all the reads, one from each of the starting positions. Okay? This is the L spectrum. The question is, if I give you the L spectrum, can you reconstruct the original genome? In other words, is there a one-to-one correspondence between the genome and the L spectrum? That's the basic question to ask in this dense read model. Okay. So this problem has been solved, actually. This problem has been solved. And I will explain to you the solution to this problem. This problem has been solved by a person named Pevman. Okay? And it's a very nice solution. And this solution to this problem will help us to develop better curves for the shotgun sequencing problem. So let me explain how this works. So it proceeds by constructing a graph. This graph is called the root graph. So here's what it does. The read length is L. In this example, it's 5. What it does is first, for each length L-1 sequence on the genome, what we call L-1 bar on the genome, it creates a node. For example, ATAP is this node. TAGA is this node. And so forth. Okay? Now, these are the nodes, but I have to create edges. Okay? Now, what we do is I'm going to add an edge between a pair of nodes, the ATAG and TAGA. If the overlap has length L minus 2, in this example, 3. So if ATAG and TAGA have overlap of length 3, TAG and TAG, I'll add the edge. That means that this guy could possibly. All right? Okay. Actually, that's not correct. This guy has to do this. Okay? Right? Because there's only one edge. Okay? So therefore, if I look at this node and this node together, if you take the union of the two, then I get a read of length L. So ATAG, TAG, if I combine the TAG, I get ATAGA, which is read of length 5. So therefore, each read corresponds to an edge on this graph. Okay? So now, what do I want to do? I want to reconstruct the original sequence, which contains all these reads of length L. That is equivalent to, I want to find a path which goes through this graph that covers each edge exactly once. That is the algorithmic problem, right? Because a sequence is the underlying sequence. It has to contain each and every edge, because it has to give rise to all the reads. And it has to contain exactly once, and not twice or 3 times. Okay? So therefore, I need a path which goes through all the edge exactly once. And this turns out to be a standard graph theory problem. Finding a path that covers every edge. It's called, do people know this algorithm? Well, it's a famous history, right? It's invented by this guy, Euler. Euler is the wrong way of pronouncing his name. And he had this idea. I think the history of this came from the fact that he wants to cross all bridges in this place called Königsberg. It's a Königsberg. He wants to cross all the bridges exactly once. He wants to cross all the bridges, but he doesn't want to waste any extra effort on crossing a bridge twice. Okay? And that's how he solved this problem. And it turns out that which two nodes? AGCC and GCCC. AGAC should go to. This is wrong. This is wrong, right? This doesn't make sense. Very good. Very good. So this is correct. Oh, this is not correct either. So what should it be? Let's see. AGAC should go to GACG. So I believe this should be GACG. So there should be two nodes. Okay, good. All right. Let's try to fix it, just to make sure we understand it. Okay. So there are two nodes that follow AGAC, right? Because in this example, AGAC appears twice. It's a repeat of length 4. One node is AGAC. Okay, it's followed by GACC. Correct? But it's also followed by the second copy is followed by what? GACG. Okay, good. So GACG is followed by what? GACG is followed by ACGA. Okay. And GACC is followed by ACCC. Right? I think these two are just one. Is it a fixer? No, I don't know how to fix this. There seems to be a bit of a mix-up there. GACC. Okay, so can I replace that one, the upper one, by GACC, and then ACCC, and then CCCT? Yeah, I think I need to fix two nodes up there, and I could fix GACG here and ACGA. Yeah, so I'm sorry. So those two nodes and those two nodes have been replaced by those four nodes over there. Is it okay? All right, good. The wrong one.
I guess probably have to implicitly assume that each element
What? Well, I didn't mention.
So if you make it up, you don't really know whether you're
Yeah, here I'm assuming you do. Here I'm assuming it's directed. You know the beginning, you know the end. Yeah, so in practice, there's another complication, but we're just not considering this model. But just to simplify things, we know the so-called free prime right 5 prime. We know the beginning, we know the end. Okay? All right. So the Eulerian. So can anyone tell me what's the Eulerian cycle in this example since we added? We start with ATAG. We go here. We go here. And then where do we go? We go down or we go up? We go up. We come back down. And we come back down. All right? So this is the Eulerian path. We have resolved the repeat. So we have a repeat of length 4 here. And we resolved it using read of length 5. Although we cannot bridge. So the read of length 5 cannot bridge repeat of length 4. Right? But yet we resolved it. And that's because we used the Eulerian cycle. So the fifth, in general, the theorem by Pevner is that if the read length is greater than the interleaved repeat, the longest interleaved repeat, and the longest triple repeat, then it brings up as a unique Eulerian path, which is the original genome. Okay? So this result, together with the early result I mentioned of the necessary condition, says that L greater than this is necessary and sufficient to reconstruct. And so therefore this number is the critical read length of the genome. And this is tight. So let me write that important fact down. L critical is equal to the maximum L interleave and L triple. Okay? So that's what is established. The necessary condition and the sufficient condition by Pevner. Okay. All right. So this is for the dense read model. So let's take a little break now. Our copy. And then we will come back and see how we can apply this result for the shotgun model. More work is a little bit more work is needed. So how long should we